So last segment, we saw a specific example of dynamic programming in action for the problem of locating K stations to serve N towns on a rail line. We tried to abstract away from that example and to understand the general reasons and principles for when dynamic programming will work. So because we will be now confronted with other problems and we have to decide if dynamic programming can be used or cannot be used. So one thing that is important for dynamic programming to work is something called optimal substructure. What that means is that in order to solve the whole problem optimally, we need to solve certain sub-problems optimally. Specifically in the case of dynamic programming, I told you that one way to think of dynamic programming is to ask a good top-level question and explore all possible answers to that question. In the case of the station location problem, the top-level question was, for what value of I? So how many of the towns will the first station serve? Will it serve I towns, but what value of I is best? So that's the top-level question. And we explore all possible answers, meaning all possible values of I. So we say, could the first station just serve one town? Could it serve two towns? Or all N towns? So we try all possible answers. So we have that top-level question. And so once we ask that question, we decide to explore one of the answers, that is that the first station will serve I towns. We nibble away the first I towns, and we have to recurse on the remaining subproblem, which is from town I plus 1 through N. Optimal substructure says that you really should be solving that remaining subproblem optimally. It doesn't pay to do it suboptimally or worse than optimally. Basically, sometimes you might imagine that by solving one piece of the problem less than optimally, you benefit greatly on another piece of the problem. That doesn't happen for any problem where dynamic programming is applicable. Whatever subproblems we create by nibbling away some piece of the original problem, we really need to solve optimally. The other key point that made dynamic programming efficient was that we didn't have to solve too many different subproblems. Even though in the recursion tree picture we seem to have a lot of subproblems, we realized that many of them were the same. The same subproblems were repeating time and again. And in fact, the number of distinct subproblems we had to deal with was rather small. So this is a key feature, not too many subproblems, that makes dynamic programming work. So whenever a problem has something called optimal substructure and not too many subproblems, then we can use dynamic programming. So another example of optimal substructure that I think is a little bit more intuitive is the following. Suppose we want to find the shortest path between two cities, A and B. And let's denote the path a going through a path going from A to x1 through x2 all the way to B by this notation A squiggly arrow B. That's a path from A to B. We want to find the shortest path. And suppose I know that the shortest path from A to B passes through a city called C. So C is definitely known to be in the middle of the shortest path from A to B. So that means the shortest path from A to B is actually comprised of two paths, a path from A to C and a path from C to B. What does this tell us about the shortest path from A to B? So what we know is that the shortest path from A to B better take the shortest path from A to C and the shortest path from C to B. Okay? Because why would you take a slightly longer path from A to C? If you did, it would only make your path from A to B worse, because you could replace the longer path from A to C by a shorter path. So this is a very simple idea that you have optimal substructure here, because in order to solve the whole problem optimally, we need to solve the two subproblems, the A to C problem and the C to B problem optimally, assuming we know that C is on the shortest path from A to B. So shortest path has optimal substructure. A related sounding problem called the longest path, trying to find the longest path from one point to another, which never goes over the same point twice. that problem does not have optimal substructure. Even if I know that if I want to go from point A to point B, and I know that point C is on this longest path, it's not the case that the longest path from A to B is made by making first the longest path from A to C and then making the longest path from C to B. In fact, sometimes you may have to take a shorter path from A to C in order to get the longest path from A to B. So I won't explore that further, but I'm just saying, I wanted to say that optimal substructure is not something that happens in all problems. It happens for certain problems. So we saw the shortest path from A to B has optimal substructure, but the problem might be that even though it has optimal substructure, we have a challenge finding the point C in the middle. If we could find that point C that lies on the optimal shortest path from A to B, we could reduce the problem of finding the shortest path from A to B to smaller problems of finding the shortest path from A to C and from C to B. And what dynamic programming basically does is, because it's difficult to find C, it looks at every possible C and says, if C is on the shortest path from A to B, then what would the shortest path look like? And then it takes the best C it can find.